Finding z-scores given mean and standard deviation of the population. Uh, in section 2.3, we looked at measures of center, so finding where the middle of a data set was, and in section 2.4, we were looking at measures of spread, or seeing how spread apart our data set was. Now we're going to look at individual values within our data set, and using both the mean and the standard deviation, so a measure of center and a measure of spread, we'll be able to describe where a data value is. So think back to the last section where we looked at the percentage of data that falls within 1, 2, or 3 standard deviations of the mean. So think about what that percentage is. All right, we looked at this chart in the last section, and this chart showed us the empirical rule, where we have, let me see here, we have 68% of the data falling within 1 standard deviation of the mean. Then we had 95% of the data falling within 2 standard deviations of the mean, and only 99.7% of the data falling within 3 standard deviations of the mean. So once we go out 2 standard deviations of the mean, so looking at this one right here, we have the majority, nearly all of our data values right there within 2 standard deviations of the mean. Right? So when we move on to this section and looking at the standard score, the z-score, we're going to stick with that idea where most of our data set falls within 2 standard deviations of the mean. Right? So looking at the standard score, or I'll commonly call them z-scores, they represent the number of standard deviations that a given value is from the mean. So now we sort of use standard deviations, and we set up this ruler that we can change for different data sets. Right? The increments on this ruler are the standard deviations of that specific data set. Right? The formula for finding a z-score is right here. It is z, which will be our variable to represent the z-score, equals the value minus the mean divided by the standard deviation. And in symbols, that's just x minus mu, all divided by the lowercase sigma. So just looking at that formula and thinking about the empirical rule, here we have a chart showing unusual versus usual scores. So our usual scores right here, they fall within 2 standard deviations of the mean. Right? And a z-score will tell us how many standard deviations away from the mean that data value is. We have unusual scores between 2 and 3 standard deviations away from the mean, either in the negative direction below the mean or the positive direction above the mean. And finally, our very unusual scores are outside of 3 standard deviations from the mean. Now, a couple things to think about with the z-score. The way the formula is set up, we take the value minus the mean and then divide by the standard deviation. So we take our data value, or the x, and find out how far away it is from the mean by subtracting the two, and then we divide it by the standard deviation to get kind of this standard distance in relation to the data set. So this means a z-score equals 0 for a particular data value. That data value is actually equal to the mean of that data set. If a z-score is positive, right, that means that data value is greater than the mean. Right? So looking back at this chart, over here are all of our positive z-scores, where 0 will actually equal the mean of that data set. So then a z-score that is negative means that that data value is less than the mean. So that data value would be over here to the left of the mean in the distribution. Let's use this formula now and look at some examples with calculating z-scores. So in example 1, we have that a distribution has a mean of 23 and a standard deviation of 4. We want to find the z-score for the value of 31. Right, so let's look at our z-score formula. Z equals the data value minus the mean, all divided by the standard deviation. Within the problem, so let's highlight the key information. A distribution has a mean of 23 and a standard deviation of 4. We want to find the z-score for the value of 31. So just looking at what the problem gives us, a mean of 23, right? Our symbol for mean is mu, so I'm going to label it. A standard deviation of 4, so I'm going to label that with the lowercase sigma. And finally, a value of 31. I'll label that with x. So now, everything's labeled, I can just substitute it into the z-score formula. So I have 31 minus 23, all divided by 4. Right? So doing the math real quick, this comes out to a z-score of 2. So this means the data value of 31 is 2 standard deviations above the mean, or it's 2 standard deviations above the 23 for the data set. So example 2 is looking at a distribution with a mean of 16 and a standard deviation of 2.5. Now we want to find the z-score for the value of 14. Just going through the problem again, I'll highlight the key information. Right? The distribution has a mean of 16 and a standard deviation of 2.5. We want to find the z-score for the value of 14. Right, so let's label that key information with the variables now. A mean of 16 is mu, the standard deviation of 2.5 is sigma, and the data value of 14 is x. So I'll write down my z-score formula again. That's the data value minus the mean divided by the standard deviation. Substituting values in, I have my data value of 14, the mean of 16, and the standard deviation of 2.5. This equals a standard deviation of negative 0.8. I'm sorry, that equals a z-score of negative 0.8. So this data value is less than 1 standard deviation away from the mean in the negative direction. So it's to the left of the mean, it's less than the mean, less than 1 standard deviation away. So this is a very typical value, right? There's nothing unusual about 14 in a data set with a mean of 16 and a standard deviation of 2.5. All right, next here is an example with a context to it. When Helen Mirren won the Best Actress Oscar in 2007, she was 61 years old. Now, the Oscar-winning Best Actresses have a mean age of 35.8 years and a standard deviation of 11.3. So before we get to the z-score, let's first find the difference between her age and the mean age. Right? In part A. So I'll highlight some of the important information in the problem again. She won her Best Actress Oscar in 2007 when she was 61 years old. And then the Oscar-winning Best Actresses have a mean age of 35.8 and a standard deviation of 11.3. So if we want to find the difference between Helen Mirren's age and the mean age, then we can just subtract them. So we take her age minus the mean age, and that will equal 25.2 years. So to find out how many standard deviations this difference is, we just take her difference, or the difference between her age and the mean, and divide by the standard deviation. So we'll divide by 11.3, and that equals 2.23. Now if we want to convert Helen Mirren's age to a z-score, I'll use the z-score formula, where z equals the data value minus the mean divided by the standard deviation. Going back to what I highlighted in the problem, her age is the data value, mean is our mu, and the standard deviation would be our sigma. Alright, so our data value is 61, that's her age. The mean is 35.8, and the standard deviation is 11.3. Alright, now this calculation also comes out to 2.23. So Helen Mirren's age has a z-score of 2.23. So that's 2.23 standard deviations above the mean. So in Part D, when we want to consider if this is an unusual age to win a Best Actress Oscar, we would have to say yes. 61 is unusual because it is 2.23 standard deviations above the mean.